This is the 2020 testing tips and advice for the upcoming AP exam. This video, I'm just going to go over the first page and do a second video for the second page. A couple of definitions, descriptions of common AP calculus exam terms and phrases that I just want to go over, and also just maybe point out some examples. Let g be a twice differentiable function. That just means that we're talking about a smooth curve. That just means also that the second derivative is not going to be a zero. It's going to be at least degree 2. So that means if you find the second derivative, it'll be at least a constant that's other than the 0. So 3x, for instance, is a linear graph, is not twice differentiable because the second derivative is going to be 0. So basically, twice differentiable function, just a curve that either x squared or higher. Differentiable function, it's a smooth curve with no sharp turns. So that just means that our derivative is going to exist at every point on the graph, and there's not going to be any sharp turns like absolute value function. Third term you may see differential equations. This is just referring to, this is just a name that refers to an equation that is in the derivative form. So anything that has a derivative variable in it, like y prime is equal to 3 minus y times x, or d2y where dx2 is equal to 3x, anything that has a derivative variable in it makes it a differential equation. All right, find the solution to a differential equation. That just means that we have something in the derivative form, and we want to eventually work our way up to solving for that variable y to get rid of the derivative form. So what we're going to do is we're going to take the antiderivative of both sides. Sometimes that requires us to first separate the variables. So we've been practicing a lot of problems recently with solving differential equations. So hopefully we can be comfortable with that. Find the equation of a tangent line. So this just means that we need to gather enough information to put it into point-slope form. The information that we need are ordered pair, which is the point, and then the slope, which comes from the derivative or the dy dx equation. So if we have a y prime equation like this, we can take the ordered pair, plug in, find the slope, take the ordered pair that the problem gives you, then you put in the point-slope form, and then finally you're going to take that, once you find that tangent line equation, then you're able to produce what the problem is asking for. All right, number 7. This one is let uppercase h be the antiderivative of f. So when this wording, when this phrasing is given, this is basically a long way of saying that f is really h prime. Okay, because if h is the antiderivative of f, what that's really saying is that f is sitting at one level below h. It takes the antiderivative of f in order for these two to be at the same level. So if you see this phrasing, that just means that if you're looking at the f graph, you're really looking at the h prime graph. This is just another way of saying that your f is really the h prime graph. Okay. All right, statement number 8, find the absolute maximum or minimum. So the words absolute is an indication that we're going to be applying extreme value theorem. So anytime we're looking at a graph, the only candidates that we have to be concerned about if we're trying to find the absolute max or absolute min is we have to consider endpoints and we have to consider critical points. So critical points is either where f prime is equal to 0 or where f prime is undefined. Okay, so once we identify our critical points and endpoints, then we're going to plug them all back into the original equation, and whichever has the highest or lowest value is going to be your absolute max or absolute min. Statement 9, find the instantaneous rate of change. This just means to find the derivative at a point. So if the problem says given x of t is the position function of a particle, what is the velocity of the particle at t equals 5? So that means we need to find the derivative of that position function, get it to the velocity, and then use the velocity to evaluate evaluate the velocity at that point. Statement 10, find the average rate of change. So if I want to find the average rate of change, I'm going to be taking the slope between the two endpoints. So I'm just using the slope formula. There's no derivative. So for instance, if I want to find the average velocity and the information that's provided for us is the position function, then we just take the change in position over change in time, and that will give us average velocity. So notice that average velocity starting from position is different than how we approach velocity starting from instantaneous velocity starting from position. So here, with position, we need to find the derivative. Here, we take position. We start with position, but we don't find the derivative. We just do slope, change in position over change in time. When we see a related rates problem, we know that we're dealing with the related rates when you have wordings like find the rate at which the area of the circle is changing at that time, or beach ball is deflating at a rate of 10 cubic centimeters per second. So anytime we see time involved and their motion and time involved, we know we're going to be seeing related rates. So the big idea with related rates is you're going to be finding that you're going to be starting with an equation that is in a geometric form or algebraic form, and you're going to be finding the derivative with respect to each variable. So for instance, let me give some examples of that. Some related rates starting points could be Pythagorean theorem, it could be a trig equation, it could be a volume equation, but all in all, we always start with our algebraic or trig or geometric equation, and then we find the derivative. And when we find the derivative, that is when each variable's d over dt is going to pop up along the way. Okay, so theta produces d theta dt, y produces dy dt, r produces dr dt, or v becomes dv dt. So we have to make sure that we're able to identify that step, and then after this, then it's just a matter of reading the problem and taking the information and plugging in and finding the appropriate variable that the problem is asking for you to solve. Number 12, this statement says, at what time does the instantaneous velocity equal to the average velocity over the given time interval? So this is a way of showing that the problem wants the student to be able to identify this as a mean value theorem application. So the average velocity is this change in position over change in time, and the instantaneous velocity is this f prime of c. So we basically, we're going to be taking the slope between the endpoints. We're going to take the derivative, or take the velocity function, set them equal to each other, and then solving for either t or solving for whichever variable the problem is asking for. Statement 13, use the data in the table to approximate the rate at which the temperature is changing. So this means to take the two closest order pair temperature values and find the slope. So if we're asking for the rate of change that the temperature is changing, it's just change in temperature over change in time. So if we don't have the function available and we're only dealing or starting with order pairs, then the best we can do is just take the slope between endpoints. Notation, d2y over dx2 just means find the second derivative. All right, statement 15, when you approximate values using Riemann sums, which is just basically finding area approximation using rectangles, or we can also put this in with trapezoids as well. So basically, when you're dealing with Riemann sums, the units of measure is going to be changing. Okay, so if the values in the table are in terms of gallons per hour, then after Riemann sums, your units will change because you've accumulated those rates over the period of time. So the gallons per hour is now going to be total gallons, okay, or just gallons. An example of this could be a word problem. For instance, this one here. If we have order pairs that are in terms of hours and inches per hour, that if this is representing the rate at which snow is falling, then if you were to accumulate the rates over the period of time, it's no longer going to be our units is no longer going to be inches per hour. Okay. Once we accumulate these rates over that time period, it's now going to represent the total inches of snow that falls in that time interval. Okay. Also, bottom of this page here, be able to recognize when the problem is wants you to apply certain theorems. So, first theorem of calculus. If a problem says find the definite integral from 0 to 20 of w prime of t, and you're only given w of t function, then we have to apply our integral process and use w of t, because we know that the integral of w prime is going to turn into w of t minus w of a. So for instance here, just to show the application here, if I have the definite integral from a to b of f prime, okay, that's going to produce f of b minus f of a. So if we push an f prime through the integral process, that f prime is going to move up one level to f of x, and then once we have that, then we plug in our upper bound minus lower bound. Same idea here, the integral from 0 to 20 of w prime, we can think of this in terms of w of t, because the antiderivative of w prime will push it up to w of x or w of t, and then we can plug in our upper bound w of 20 minus w of 0, lower bound. Right. Here is an example kind of showing through that process here. So I want to show that distinction. Sometimes we use Riemann sum, sometimes we use first fundamental theorem of calculus. It really depends on what you're starting with and what the problem is asking for you to find. So here, let's say w prime represents the rate at which waste is being added to a landfill after the year 2000. It says, approximate the definite integral of w prime using left Riemann sum in 3 subintervals. What are the units? And if we accumulate these rates over the period of time, then our tons per year is going to change into overall tons. And we go through Riemann sums, left Riemann sum, so width times height, width times height, width times height. Okay, 345 tons of waste accumulates over that time period. Now let me show you a similar problem, but with a very different approach. So let's say, again, we're dealing with waste in a landfill, but now instead of w prime, now the problem gives you the actual amount of waste in that particular year. So if we also want to find the integral, this problem is also asking you to find the definite integral from 1 to 10 of w prime, but our approach is going to be different because here we don't have to accumulate the rates. We're not have to find the exact. We're not going to have to find an approximation because we already have the waste amount in the table. So how do we do this then? So what we need to do is we're not going to be able to use w prime because we have nothing here that is in terms of w prime. So we're going to move our w prime up a level to w of t. So we're going to go through our antiderivative step. W prime becomes w of t, and then we do w of 10 minus w of 1. And now we have something that we can use from the table. 1750 minus 1400, that gives us 350 tons. And now this is no longer an approximation. This is an exact value. This is the exact amount of waste that has changed or that has increased from year 1 to year 10. All right, so back to the advice sheet here. Second theorem of calculus, we have to be aware of that. That is just really taking the application of derivative integrals and understanding the fact that if we put two inverse processes on top of each other, they're going to find a way to cancel each other out. So if I want to find the derivative of a definite integral of a function, these two operations undo each other. The only thing that remains is that this upper bound gets plugged into that variable, and then the upper bound is affected by the derivative in the end with the p times p prime. So an example of that could be this problem here. So if I let h of x be 3x plus a definite integral of 1 to x squared of g of x, and it's asking for me to find h prime of 2, I first need to find h prime of x. So 3x becomes 3, but if I want to find the derivative of this expression, I have to go through second theorem. So second theorem, I'm going to take the derivative of the definite integral of a function. So second theorem says, okay, you're not going to make much changes to this g of x. You just have to plug this x squared into the variable and multiply by that x squared's derivative. So when we do that, when we plug that x squared in for t, we get g of x squared multiplied by the upper bound's derivative, so times 2x. So here's our derivative function. Okay. Product rule, quotient rule, okay, and chain rule as well. I'll go through that on the next page. Something I stuck in here is if a problem is showing you some sort of a limit problem, then consider the possibility that it could be asking you to go through continuity conditions. Right? We've gone through a couple of example problems where you have to do that. Or it's a L'Hopital's problem where your initial evaluation of that expression produces 0 over 0, which gives you the freedom to then do L'Hopital's rule. And L'Hopital's rule just says you're going to take the derivative of the numerator expression and then separately take the derivative of the denominator expression and then reevaluate all your variables with your x value. And that should bring us to a real number, and that real number will represent the limit of that expression.